Good morning, everyone. Uh, I hope today is the last class on compiler design. I will to wrap up the syllabus as fast as possible. So, if we can recall what still so far we have covered, we started with the lexical analysis, then we switched to the syntax analysis, and then semantics analysis. I said that all the three phases means all the first three phases mainly finds the errors in the codes and report to the compiler that what type of errors actually it is written in the code. And subsequently the errors are being removed from the code by the instructions obtained from these three phases of the compiler. Now the last three phases, that intermediate code generation, code optimization, and final code generation, they actually mainly operates over the code, actually not operates, I should say. Actually, the main task of those phases are to optimize the codes and to generate the machine level codes. Correct. So we will try to loop through those sections. This session may get quite lengthy because I have to cover those portions as well. And those portion means the final stage we will not be covering that final code generation, because final code means it is a machine level code or the microprocessor level code, 8085 or 8086 microprocessor code. So those are part of microprocessor. How to move. I hope, I don't know whether you have gone through that paper microprocessor or not. Some LD load command, move command, MVI commands are there, store commands. So those are the parts of the microprocessor level codes. Correct. So mostly we will be focusing on intermediate code generation and code optimization. Okay. Now I hope you can see the screen. Let me enhance the brightness of the screen. Okay. Now, first you see that in the semantics analysis, what we have seen that already uh, corresponding to uh, corresponding to a syntax tree or abstract syntax tree, the value is being evaluated, right? Now, in intermediate code generation part, mainly the first purpose here, just first I'm showing here, then I will be moving to the document, that in the intermediate code generation segment, what they actually mean perform, that they try to optimize the graph. So this is the tree that you are looking at here. This is the tree, you can assume it is a complete syntax tree, right? Now this syntax tree to be optimized using the method of directed acyclic graph technology. Technology means the platform, correct? So why they are doing so? Because they want to minimize the tree, so that once I will be moving to the microprocessor level code generation, so minimal number of codes are being originated, right? Now I hope you can see here that it will be good if I let me go to this picture over here. Okay, uh, delete this portion first. Okay, just I'm copying this image in that Word document so that whatever I write there you can see it clearly. Okay, okay, I have pasted it. I hope you can see it now. Now you see that in this document, that here let the expression is given a equal to b asterisk c, this is minus c, plus b asterisk minus c. This is an expression given, right? Now corresponding to this expression, what I can do, or what already being done by the syntax tree, is that this is a syntax tree being formed. This is a syntax tree, correct? A equal to, if you drop the values perpendicularly over here, so this is a, then this equal sign comes, then this B comes, then star, then C, then plus. In this way, all the operator comes, correct? Actually, the minus operator is there. So C is in the right side of, like that. I should write in this way. So that C value will be coming. First the minus will come and then C value will come. So that means if I convert it in infix or in order expression, then I will be obtaining the equivalent expression, right? Now, in the intermediate code generation phase, what we are doing, you see that these part are same, B star minus C, because you see B star minus C is repeated twice, B star minus C. So I am multiplying B with the negative value of C. So if I can make a single graph out of this, already this complete syntax tree is being formed at the end of semantics analysis. An expression is being generated, this expression. Now, if I can form a minimized tree, then it is possible to generate minimal number of codes. Let us see how it is possible. So the same A equal to, it remains same, A equal to, then plus operator comes here. So here I am putting a cyclic sign. You see that here, though they are not complete cycle, actually here one arrow is coming here, here another arrow is coming, because both are marching over here, and here the expression is B star B asterisk minus C. So that means I wanted to mean that A equal to plus, then here it will be taking B star minus C, and another sense the star will come, because you just see A equal to, let me change the color here, it is first it is taking A equal to plus A, not plus, actually coming later, because I have to drop the node perpendicularly here. A equal to, so A is dropping here, equal to is also dropping. Then in the left side, the plus operator, the left side is, this arrow is coming. In this left side, what is the value? B star minus C. So here B star minus C, this entire node is being dropped here once again. Then the plus operator will come. This is a plus. Then again in this arc, right side of the plus operator, again B star minus C. So again the same node will be repeated here, right? So that means the entire expression is being shortened over here, right? The expression remains same, just we have shortened the graph structure. And what benefits we will be getting over it? Okay, let us see what benefit we will be getting. Let me erase this portion, and I will be writing the 3 address code back to back, so that you can understand it clearly, that how it is happening. Okay. First, see what is called 3 address code. Now, what still so far I have shown? I have shown you the tree. This is a tree, and how to optimize a tree. Our main focus is to generate minimal number of codes in the compilation phase, right? Now, 3 address codes means if I can write an expression in this way, let x equal to y operator z. For example, x equal to y asterisk z. This is called 3 address code. 3 addresses are there. For x, I need one address. For y variable, I need one address. For z, I need one address. So this structure is known as a 3 address code format. First, you need to remember. Okay, what I will be doing, I will be generating the 3 address code for the structure that I have written. Okay, now we see that first here, if I try to evaluate the code over here, I am writing the code in back-to-back mode. First, let minus C, this node value to be calculated, right? So I am writing T1 equal to minus C first, right? Then after minus C is being evaluated, then I have to multiply B with T1. I am moving in bottom-up manner. So let I am taking another variable T2, which is calculating B asterisk T1, because T1 is already minus C. This minus C is here. It is being multiplied. So that means this node value already I have obtained. Now again, I have to calculate T3 equal to, I am putting it is a minus C. tree address code, and I am taking T4 equal to again B star T3, right? So that means up to here I have evaluated T4. Okay. Now T5, what I have to do? This value is for, okay, it was minus C, no? Okay, it was T2, and this structure, this subnode was T4. So I have to add T2 plus T4 in order to get this plus operator in a single node, right? So the entire node comprises with T5, right? Then finally I am assigning A equal to T5, right? So this will be the intermediate codes or the three address codes corresponding to the tree. This is very simple. I hope there are no complexities are there inside it. Okay. Now you know that, okay, for corresponding to this tree, that tree that I have taken, the three address code, it is a three address code. Three address code, this is a tree, right? So we have another tree, the equivalent tree we have, and we will be taking the three address code here, right? Let us see what are the changes are happening. No, here first minus C we are taking in the same way, T1 equal to minus C. Then B star minus C we have to calculate. So this node value we are going to calculate, that T2 equal to B asterisk T1, right? Okay, once it is being done, that means the value is, node value is T2, right? Now you see that there is a arch, same arch is there, one arc is here, another arc is here, correct? Let I am taking another variable T5 or T3, even I can take, no problem with that. So let I am taking T3, no problem over here. T3, that means T2 plus T2, because this is a plus operator that I am taking twice. So that means the entire node value now converted to T3. Now A to be assigned to T3, or T3 should be assigned to A actually. So now see that in the previous code segment, we had to reach up to T5 variables, but here only we had to reach up to the T3 variables. So that means T4 and T5, those two variables we have not used. And subsequently, the amount of memory space that are required, that is also being minimized. Correct? So this is one phase of intermediate code generation that I want to highlight here. That after generating the complete syntax tree by semantics analyzer, then a directed acyclic graph is being formed in order to optimize the tree. And also subsequently, first the tree is being optimized, right? Let me delete those portion so that you can tell everything clearly. Okay. So the first task is that to form this tree is being formed in the semantics analysis part. In the first phase of intermediate code generation, this tree is being optimized using the direct acyclic graph, using the direct acyclic graph and the associated codes. Then once it is being done, then its corresponding three address code is being generated. Its corresponding three address code I have written out here. Already you can check later also. And also subsequently its three address code is here. So once they find that this second option is giving us the better three address code, so the second one is being taken and being proceeded to the next phase, that is called code optimization phase. Correct? So intermediate code generation phase has the task of generating and optimizing generating the three address code and optimizing the tree. We are not optimizing the codes here. In three address code, we are not optimizing. Try to understand. We are optimizing the tree. So the tree optimization is the first task. Second task is at generating the three address code. So here I am writing optimizing the first task of the intermediate code generation, optimizing tree, and second task is generate 3 address code. So this is the two tasks of the intermediate code generation, correct? Okay. Now let's see some more examples over it so that it is being clear to you. Okay, let me take some more pages. Okay. Now you see another examples also I have shown here that will be good for you to understand. Let me again copy it and paste there. Okay, here also you can see that the expression was x equal to a plus a asterisk b minus c right now. So here you see that this a is being repeated twice, right? So here also an opportunity comes that corresponding to that expression already in the semantics analysis, this tree is being formed. Correct. But as a is repeated twice, so you can expect that a is being taken here because a is here, and also I can take a. This star can take a, right? And also this plus also can take a, right? So this a actually arc is being connected over here, so that the necessity of this a is being removed, right? So that means again the graph is being optimized over here, correct? So if you optimize the graph, then subsequently you can optimizing the graph means the graph nodes here in the tree, the initially graph nodes, this node was an extra node. If I drop a node, then certainly I can expect that in the 3 address code at least one register requirement will be less, correct? Okay, now let's see another image over here. Okay, here another important image that is being given over here. Let me zoom out a segment. Okay, here also the 3 address code, back to back the 3 address code also I have shown. Okay, show once again. Okay, this portion is being taken out. Okay. Okay. Okay, here also you can see this is an expression that I have given. This is an example number 46 actually. These two examples are there. And here also another example. A equal to B star minus C asterisk minus C plus D. So in this expression, if you see that there are no common sub expressions are there. If no common sub expression exists, then it is not possible to optimize the code. Code means not possible to optimize the graph. You can optimize the graph only if common sub expressions are there. Because if you see earlier, here also the common sub expression was A and A. And in previous case, it was B asterisk minus C, it was in common sub expression. So based on the common sub expression, the tree is being optimized. So if no common sub expression exists, for example, here that we have seen, so it is not your fault to optimize. So this will be the tree to generate the 3 address code. First you see, I have written this 2-step, okay, that's 2 steps, okay, not here written. So I said the 2 tasks are there, one is optimization, another is 3 address code, correct? So the first they try to optimize the tree. If the tree nodes or the tree edges can be reduced. If it is not possible, then finally the 3 address code is being generated. And why this 3 address code is being generated? Because in intermediate code optimization phase, in the next phase is the code optimization, while we will be migrating from intermediate code optimized code generation to code optimization. Then code optimized in the code optimization process only will be considering the 3 address code. Because once the 3 address code optimization is being done, then it will be moving to the machine code generation phase.
So be clear with the idea that whatever the syntax tree, complete syntax tree we obtained in semantics analysis phase, over the tree, we are performing the optimization in order to drop certain edges and nodes by keeping the functionality as it is, if it is possible. If it is not possible, then directly we are moving to the tree address code. If the optimization is possible, then also we are moving to the tree address code. And those tree address code will be taken by the code optimizer. Correct? So we will be discussing that section quite later. Now, here you see that in the expression that I have written, no opportunities are there to optimize the graph. So directly from the graph, tree address code is being obtained. You just see over here, I have given that, say for the same expression in the back-to-back side, I have written here t equal to minus c is the first tree address code here, because from E to ID to C. So first, this is the second, means for this node actually, for this node we have evaluated. For this node actually it is not required. For this node we have evaluated, it is the T3 equal to T2 plus D, and also for this S we also have evaluated. Correct? Finally, now you will be wondering that, sir, why you have not, though S, E, and E, for these nodes we have evaluated for the red color nodes in tree address code, but why you have not evaluated the code for E, for DC, for DC, and for DC, though these are the nodes? Because tree address code means, you know, that some operators should be there. So what should have we have written here? We should have written, let T, we have taken T1 equal to ID, we should have written, and here ID equal to D, which means actually in a whole I can write T1 equal to D. But T1 equal to D is not a tree address code that we are considering, because no operators are coming. So if any plus or minus operator is there, then I can consider still it is a three operator code. Three address code. But you see in the red color nodes, this minus C is there. B starts, B asterisk T1 is there. For T3, T2 is there. Correct? So for the nodes which is not generating three address code, but definitely someone asks us to generate two address code, certainly we are considering T1 equal to D if the two address code was valid. But in respect to three address code, T1 equal to D you cannot take. So in exams, they ask a question that a expression is being given to you. They will ask you to generate the three address code. But if you write T1 equal to D, or this code you are going to write, then it will be completely wrong, because it is not a three address code. Three address code, again I am repeating, that X equal to Y operator Z. Correct? So Y operator Z means sometime if Y is void, then it is also fine, but operator Z should be there, or even Y operator is should be there. So any sort of operators is required in three address code. Right? So in similarly for this blue color node E, also you say that first I have to assign ID equal to B and then E equal to ID, which in turn E equal to B. But again you see E equal to B, this is a not a three address code, so I cannot take it. That's why directly I am taking E as a B while generating the three address code over here. Because I am taking E equal to B, I am taking B is approaching here. And also here also I am assuming that T equal to minus C is being calculated here, three address code. So that's why they are multiplying B with T1. So B is coming from there and T1 is coming from here and star is there. Correct? So B asterisk T1. So the problem comes for the leaf nodes. You have to be very cautious while generating the three address code for the leaf nodes. If no operators are coming, you cannot consider it is a three address code. Simply you have to assign the value to its parent node. Once you get an operator, then you stop it. Like here I did. So B is given to ID and again B is given to E. So I am stopping here because here we can see a nearby operator asterisk is here. So once the E node value to be calculated, definitely B asterisk some value will be there and some value is the E node value. So E node value they are taking minus C, so it is being calculated. Correct? Okay. I hope you have understood it. Now for the next example that I have given here, example number 47. Example number 47, you just see here also the same thing happens, that here e1 equal to y, here you cannot tell this is a 3 address code, because e1 equal to y, if I write this is a 2 address code, or ez equal to z, this is also a 3 address code, so I cannot write. Better to assign the value here, y value to be assigned to here and z value to be assigned to here, correct? Now for this e node, let me mark in red. When the e node value I am calculating, it will be taking y, then this plus to z, y plus z. So that is being written over here, t equal to y plus z or x plus y, whatever you want to write. So it should be y plus z, not x plus y. It should be y plus z. This is a small mistake is here, y plus z. Correct? Once it is being done, then finally no options are being left here over here for the root node. Then only x equal to t you are assigning. Correct? Because you see in the final time, now one questions may come to your mind that said you are not considering e1 equal to y as a 3 address code, but still you are considering x1 equal x equal to 2 as a 3 address code. Here actually we did not have any options left but to consider this equal sign as an operator. Here this equal sign we are putting e1 equal to y. So no one is asking you whether e1 from e1 is y being generated, but no one has said whether it should be equal sign or has symbol or some special character, right? It is possible. Here they have mentioned that this equal operator, this equal symbol is not an assignment symbol here. They ask us to consider it is an operator. So here we are writing x, this is x. Operator means here operator, and here this is here x, sorry, x equal to here, x equal to the operator, and then if the value is it coming from t, so here it is t. So here again we are considering it is a 3 address code. 3 address code. Okay. Now, what I was telling that that here this equal symbol is acting as an operator, right? Here it is acting as an operator. But here when I am assigning e1 to y, no one was asking us that there is an operator equal is there. But we are assuming that y value is supposed to be assigned to e1. Right? So there is a difference between when you are putting an explicitly mentioning an equal operator and where you are putting no explicit mentions, explicit specifications are being done for assigning a value to a variable. Right? So they are different. They have a different context. Correct? You need to be very cautious on that architecture also. I hope that your idea should be clear. Again, I am repeating here x equal to t, this x equal symbol acting as an operator. But here e1 equal to y, we know, but who asked you to put equal of symbol over here? No one, na? So how I can tell that e1 equal to y? Just we know that y value is assigning to e1. But here they are mentioning equal symbol as an operator. So that's why it is a valid 3 address code, but this one is not. But if, for example, if any equal operator was there, for example, here the operator was there, then definitely it was okay. So you could have written that u1 equal to, sorry, equal to e1 node you are evaluating. So here operator was here. So that you should have written equal to, it was e1 and y, because e1 is in the middle and y in the right side. Then it is a 3 address code, because this equal was coming here, e was in approaching middle, y in the right side. So equal to e1, it is a 3 address code. Right. So that is a different context itself. Like the same e1 is placed in the middle. Okay. I hope your idea should be clear here. Okay, now the main thing already I have said in the intermediate code generation. Uh, the intermediate code generation has the main task. Already I said that optimization in the tree level, and secondly, to convert the optimized complete syntax tree into the three address code, because we require three address code in the next level of optimization. Okay. Now we are moving to the next phase, that is called code optimization. Okay. Let me delete all the portions over here. No, okay, fine. Uh, in the code optimization, actually, uh, you see that code optimization can be done in two phases or in two areas. Either I can perform an optimization in the source code that is being written here, or even I can perform the optimization in the intermediate code. Intermediate code and source code, what does it mean? For example, when you are writing in a code that has include stdio.h, then you are writing main. Within the main you are mentioning select integer a and b, you are mentioning, and you are assigning a equal to b, correct? So here actually you can perform the optimization. So this is called the code level or raw level optimization, because you are declaring two variables a and b, but you are assigning b value to a. But why you are doing so? Rather taking these two variable, you should have taken only a single variable a, and you could have done the operations with a, right? So this is an optimization. Several areas are there, but I am giving a small example over here. So either you can optimize the code over here, or even you have seen, let for a code you have a complexity of big O of n squared, that I have a bubble sort, for example, bubble sort. You know that bubble sort has a complexity of order of n squared, right? So you know that two for loops are there. One is for I for is equal to 0 for their one for loop. For another for loop is there for j. For j, I am starting with 0, for example, or even I can start with I. That depends on me, right? Now, if someone asks you to convert whether you can reduce the complexity of bubble sort from order of n squared to then order of n or n log n. So that is a case of you are performing you are performing the optimization in the raw level code. Okay. So if the list is already pre-sorted, bubble sort means, let someone is asking you to sort this 1, 2, 3, 4, 5 in the here this is already being sorted. So from lowest value to highest value I am increasing, but they are asking you to sort it from lowest value to highest value. So you can change the code in this way, that if here in these two for blocks you can place a code. If here you can write let this is an array, a array, you can write that if ai less than aj, ai plus 1, for example, then you have given the statement continue, correct? So that means you are checking that before entering in the inner loop, you are just considering that whether these two fields, this one is less than 2 or not. If it is less than 2, yes, it is true, then I am skipping this inner for block. In this way, for 2 and 3, you can check in the next one I will be incremented. So that means you are reducing the complexity from order of n squared to order of n for a certain pattern, not for all the patterns. So this is a optimization that you are performing in the raw level code. But machine level code optimization means the 3 address code optimization. 3 address code you have seen that when I have an x equal to t2 plus t3, then t3 equal to x, or let x asterisk y. In this way, some codes are being written. Already we have obtained the 3 address code. So if we are performing an optimization over there, that will be the case we will be considering here for the final code optimization segment, right? So different categories are here. So we will be looking through all the categories, how we can perform the code optimization in those levels. These are very simple techniques. I hope you will enjoy this segment. I will try to make it in that way. Okay. Now, what are the different synergies are there? For example, code optimization have two segments. Means, okay, let me tell one thing. One optimization is called local optimization, another optimization is called global optimization. Local optimization means, let you have written 1,000 lines code, correct? So throughout the code, when we are considering and we are performing an optimization, that is called global optimization. But let these 1,000 level codes, I have separated into small blocks of 100 blocks, 100 line code blocks. And let these 100 lines belongs to the for loops. So yes, I can consider this is a block, right? So these 100 lines, it is an if else block. This 100 line, let it is a switch case, right? So if I can put the entire code segment in small blocks and I can perform an optimization in that block, that will be called local optimization. So one is called global, another is called local. Okay. Now I am moving to the next part that I thought to be discussed over here. That is what are the different categories of optimization. Okay. So the first category is remove common sub expression. Okay. So I will be discussing all the points one by one. So just you watch how I am discussing it. Another point is stop copy propagation. Another point is remove dead code from the program. Another fourth point is loop optimization. So these four type of main optimizations that mainly exist in final code level. That means in 3 address code, we can apply these four type of optimizations, right? Under the loop optimization, 3 separate segments are there. So certainly we will be discussing on that. But first, let us discuss on the main aspects, how that optimization can be done. Okay. I hope you can see the screen over here. I need to, okay. Here you see that this is an example that I have given, example number 47. Here, some 3 address code I have written out here, correct? This is block B1. And you see in the block what I have written. This is I equal to M minus 1, J equal to N. Let this is T1 equal to 4 asterisk N. This is V equal to A T1 for this is a block. Then another arrow is coming from here. It is entering to another block. So this block is B2 block. Here also some operations I am performing. And at the end of the block, there is a iteration is there. That means you can expect this is a loop. B2 block has a self loop. And based on this condition, if T3 less than V, then I am moving to go to BT. That means based on this condition, whether it is a positive condition, based on that, this loop is being iterated. Right. So here, this is I equal to I plus 1. This is incrementation. Here, this is T2 equal to 4 asterisk I. Here it is T3 equal to A. This is T2. Right. Correct. So this is one block, B1 block. Here another block is B2 block. In this way, all the blocks are there, B3 block, and the values are propagating. And for B3 block also, there is a iteration is there, self iteration. This is a B3 block. And from where the code is being written, let a graph is being formed, for example. in the 3 address code, before generating the 3 address code, you know that from abstract syntax tree to complete syntax tree is being prepared, and then from the complete syntax tree the 3 address code is being prepared, correct? So just try to assume that these 3 address code, whatever I have written, these are obtained from a 3 address code, right? And here from B3 block another arrow is there, that it is entering to B4. Here that if only if condition is being applied, if I greater equal to j, then I am moving to B6. This is the go-to functions I have applied. Then another 2 blocks are there. Here one block is coming to B5 and another block is coming from again B4 to B6. Both the blocks contain a list of operations, right? This is the list of operations containing, right? So this is a standard structure I have taken for a certain complete syntax tree from which a 3 address code is being formed, over which we will be showing the different optimization how we can perform, correct? Now, so one thing be sure that once I design this representation, correct, so the tree level no optimization was possible. In the graph level, first before tree level the raw code level optimization was there. For example, already you've seen when I'm changing the complexity from big O of n square to order of n. Okay. So first what we are checking, we are writing a raw code, correct? So over the raw code we are trying to optimize it. So changing the complexity from big O of n square to order of n, right? Then it is passing through a compiler, correct? The compiler, it is generating a syntax graph, syntax tree based graph, syntax tree. So that syntax tree is converted to directed acyclic graph code mode where the tree is being optimized, correct? Here also we are performing the optimization, and then the 3 address code is being prepared, right? So that means we are performing optimization over here, we are performing optimization over here, but now if any more optimizations can be done or not, now here we are performing that code optimization that I am discussing, optimization over the 3 address code. So raw level code optimization is over, directed acyclic graph based optimization is over. Now whether further we can reduce the code or not. So why we are trying to reduce? Because if I can reduce the number of codes, the requirement is in number of register allocation in microprocessor level representation will be less. And you know that if I can take lesser number of registers, then definitely execution of the code will be first. So definitely your motive will be how fast you can get the results, right? So that's why this optimization is being required. Okay. Okay. Now, as I was discussing that these examples I am taking as a standard example and different blocks are there. Just try to see here that B1 block, B2 block, B3 block, another block is B4, B5 and B6. Total this 6 blocks are there over which we will be performing the optimization. I will be picking up a block and trying to show you that how optimization is being done. Okay. Let me okay. Let me copy some of the portion from here to there. I am copying this B5 block and B6 block to my Word document so that you can see over here. Paste here. Okay. Need to place one more picture over here. This one is also being required. The first technique we are going to apply, common sub-expression elimination. back to back I have placed. Now I hope that you can understand that what I was telling, that I have taken this B5 block and B6 block which was connected with this architecture. You can remember it was coming to from here to here, it was B4. Here from B4 one condition was there. So let me perform the local optimization, not go global, block by block optimization. And once the local optimization is being done, then I'll be moving to the global optimization. In the B5 block, you can see that 4 star I is here, again 4 star I is here. So the common sub expression elimination, just you see the first level of optimization that I was telling, the first one, common sub expression elimination in the 3 address code. Okay, so 4 star I is repeated twice. Even 4 star J, this is repeated twice. 4 star J, and here also 4 star J is repeated twice. Correct? Now, so these two can be merged in a single code. These two can be merged in a single code, right? In the same way, here also 4 star I is there. 4 star I is there. These two can be moved in a single code. Here also 4 star N, and here also 4 star N is there, which can be moved in a single code, right? Now any other optimization is possible. Okay, let me check. T14 AX equal to A. Yeah, here there is one optimization is possible. You are assigning, so that optimization I will be showing later. But here just I have given that after removing the common sub expression from block B5 and B6, this will be the structure. From the block B5 and B6, this will be the structure. Some more optimizations are being done, but for your understanding purpose, just I am not showing all the steps. For your understanding purpose, only some of the examples I am taking and I am explaining here. Okay? So this was the entire architecture. No? B1 was here, and then from B1 it was B2 was coming, and again over B2 one loop was there. It was B3. Here it was a loop over B3. Correct. So after removing the common sub expression that I have highlighted over here, the code is being optimized in this level and to B5 and B6. Also intermediate, what are the optimization that I have performed over here? This is for B5 block and this is for B6 block. Just you can check in your copy also later when you have a time that this optimization is being performed. Okay. So why we need different optimization? Means common sub expression elimination, loop variable elimination, because I cannot be fixed over a certain optimization. My purpose is to reduce the number of registers requirement in the microprocessor level code generation. Correct. So here that's why I am using the first stage of optimization, that is called common sub expression elimination, and I have reduced the block size of B5, which one was a lengthy one, from less lengthy one to this 3 code, 1, 2, and 3 codes. B6 is contain the 4 codes, right? Okay. Now next optimization. Let me take the screenshot of the second one. That is called stop copy propagation. Okay. Now see, this is a stage from where I left out, that this was a stage. First stage, it was common sub expression elimination, the first stage, right? And after the common sub expression elimination, the output was this one, right? This was the output. I'm removing the rest of the structure so that you can correlate all the events one by one. So this was a structure, correct? This was the B5 structure and this was the B6 structure. Now we are employing copy propagation methodology to stop the copy propagation methodology in way to further reduce the structure that I have obtained here, right? So what is the copy propagation? Copy propagation means, you just see whatever I have pointed out here, that if I am assigning, just see over here, A equal to B, that means I am assigning a B to A, right? I am taking another variable C, I am again assigning the value of A. So that means a chain system, I am putting a value B to A, then A to C. That means B value is given to A, then A value is given to C. But rather, if I read, if I requires, then if I can write the code in this way, that A equal to B, and why not C equal to B? If I need two different variables, correct? I need two variables, then why again to fetch it? Now you will be asking me, or you have a doubt that both are same. No, not both are same. Because in the microprocessor level, when you are putting a B value to A, then you can assign it. Fine. So in the register, currently the value is B. Now, in the second operation, you have to put a value of A to C. That means that register R, which was containing B, to be swapped with the value of A. So that means again your A value to be fetched, and you need to put this A value to R. Then only you can put this A value to C. But here the scenario is different. B was in the register, and again the same register is being used here, and it is being assigned to C. Correct. So that means there is no opportunity to fetch, or there is no issue to fetch the A value again to register R and to assign it. So I am reducing a CPU cycle by stopping this copy propagation. I hope you have understood. Again, I am repeating, if you have not understood it, that A equal to B, if I am writing A equal to C, the first operation, the B you are moving to A. So this B value to be stored in a register R. That value I am storing to A. Now let I have a single register. Now you are putting A value to C. That means that register value now to be swapped with A. That means from this A database or repository, again I have to move the value to A. For this I need a CPU cycle. Then only A to be assigned to C. But had I written the code A to B and C to B, then for B I had a register R, and the same register I can access here to assign to value to C. That means I am stopping the copy propagation, correct? So this is a way where I am achieving the goal. Okay. Now see, here the same thing is happening. If you see the code, x equal to T3, and again this x is being assigned over here. So this is an x and here is an x. T3 equal to x and x. I hope you can understood it. Here also it is same. Here is x. Here also it is x. I need to stop it, right? So that means x equal to T3. This should be T3 as per your understanding. And here also it should be T3 as per your understanding. Once it is being done, that means I am stopping the copy propagation. Okay. Just see that thing I have done here. So here it is T3, and again it is T3. Here it is T3, and here also it is T3. Right. So that means I have stopped the copy propagation. So initially I had given a block. Over that block, I have used the common sub expression elimination methodology. I have reduced the common sub expression part. Then I have taken the resultant structure. Over it, I have used the stop copy propagation method, and certainly I can stop the copy propagation. Now, when you stop the copy propagation, let me copy the second segment. I can show it again to you. Okay. I need to take it here. I'm taking this one, not the other. Okay. Now the next phase was a date code elimination. So I was there in the last phase, that is stop copy propagation, correct? This was the second stage. First stage was here, stage number 1. Already I have marked. Now at the end of second stage, this was the output. You already have seen. Now once you apply the stop copy propagation, date code is being generated. Date code. What is date code? For example, in a C code you are writing, you have declared a variable integer a, b and c. Throughout the code, you have used the variable b and variable c, but never you have used the variable a. If it is the case, then then কি হলো বলো?
মানে সেই ক্লাস করছি না তো
একটু okay. Sorry for the disturbance. Okay, I was okay. What I was telling. I was telling that what is the date code. Now, if I'm using B and C throughout the code, but never I'm using A, so A turns out to be a date code, right? But how to identify the date code in a? This is a date code I have written in a raw code, correct? No? So the raw code, from the raw code segment, I can find the date code. But from 3 address code to find out the date code, it is tough. Correct? So because I need to find out which assignment I have not used. Now you see in the stop copy propagation part that this structure was the resultant output structure, correct? Now once you please try to find out here that x equal to t3, this first assignment I am marking, but had I used this x variable anywhere in the place? No, never I have used. In the same way, x equal to t3, have I used it anywhere? No. T3 is being used, but ax is never used. So this is a date code that I have obtained out here. This is a date code and this is a date code. But if I take the earlier scenario, here it was not a date code because x was here. I was using x. Here also I was using x. Before the copy propagation, before we applied the stop copy propagation method. Right. Now, what happens here? That if you apply the stop copy propagation, then definitely you should be very sure that date code will be generated. So here it was not a date code. Here it was a live code. But once you apply the stop copy propagation method over here that I have explained just before, or even here also I have explained, a date code is being originated. This first code segment and this code segment. Just you check, here I have pasted it, and both the code are deleted here. This is deleted and this is also deleted. So this is called the date code elimination, right? So what still so far we have seen? We have seen the copy propagation, how the common sub expression can be eliminated. Then we move to the copy propagation, how we can stop the copy propagation. Then we have seen if we stop the copy propagation, then how a date code can be originated and how we can remove the date code. Next, we are moving to the next part. Okay. Next part is loop optimization. Okay. Let me explain over it to her raw code so that you can understand it clearly. You see, in the fourth case, that is called loop optimization. So let it is D and loop optimizations I am performing. Now under the loop optimization, several segments were there. If you can recall the PDF document that I had shared initially, that under the loop optimization, some code motion, strength reduction, and induction variable elimination, these three sub stages are there. Correct? Let us check one by one all the subsequent stages. Okay. Now loop optimization means try to understand in row level code so that you can make it relevant to the 3 address level code. Let here I have written a code fragment while this is while I less than limit -2, correct, and I am performing some operation. Is there anything wrong in the code? No, because some codes are here, but the problem is definitely corresponding to this code 3 address code is there. I could have discussed over 3 address code, but I thought to discuss over this raw level code because you can take it easily. And but be sure with that, here whatever the optimization I am discussing, the optimization is not over the raw code, it is over the 3 address code. Not raw code, it is over the 3 address code. Fine. Now you see that here I equal to limit -2. That means every time this loop is executing, I have to fetch the limit value and I have to subsequently calculate the limit -2. Right. So that means limit -2, this value every time I have to calculate, which thereafter will be checked with whether I less than limit -2 or not. Right, because if I am performing this operation, this expression evaluation, while I'm evaluating this expression limit -2, definitely requires some times. So I am wasting some CPU cycles over here. Correct. It will be a good sense if I can move this limit -2 out of the code. So that I have done in the second stage. Just see over here that I have taken a variable t and this limit -2 I have calculated prior entering the loop and I have just given I less equal to t. It is better because limit -2 it will give you a constant value. It is not give you a dynamic value. So if I place this static code out of the loop, and you can be sure with that though no limit operators are here or limit variables are here, I should say, inside the code block. So certainly if I can move out this static assignment, I can save some CPU cycles in my code. Right? Okay. But again, I am telling whatever I have said over here, the loop optimization in the code motion segment, it should be performed over the 3 address code, not over the raw code. Though I have explained it over a raw code, but it's subsequently to be converted into this 3 address code and to be taken care of. Okay. Now the next movement. Just please wait for a minute. Okay. So I was discussing on some okay, so copy propagation already I have completed. Okay, date code I have checked, and now strength reduction. Yes, the next page. It was on B3 block, right? Next page, it was I have discussed. This one is I was discussing the loop optimization. The first phase under the loop optimization was the code motion. Second phase is strength reduction. Right. Okay. Now, how this strength reduction is being done? Just see that B3 and B. This is a B3 code block. I hope you can remember. Let me show it once again from the main code. That this was the B3 code. This was the B3 block, right? This was the B3 block, correct? Over these 4 commands are written because I am considering now the B3 because already I have performed all level of optimization over B5, all level of optimization over B6. I have applied the first 3 optimization, common sub expression, then copy propagation, stopping, dead code elimination over all the blocks, but it actually works on B5 and B6. So it is being fully optimized. But now when I'm applying the loop optimization, because here in the B3 block, it has a loop. So when I am performing the optimization, I find it out that some scopes exist over B3 where the optimization is possible and in terms of strength reduction. Okay. Strength reduction means you see in the B3 block, some 4 codes are there. This is 1, 2, 3, and 4. But let these 4 codes, if I can move some code out of the block, what does it mean? It means you know that a asterisk not let 4 asterisk 5. What does it mean? It means you are adding 4 plus 5 times. Right? So you are adding this 5 with 4. 4 into 5 equal to 20. And you need to repeat this 4 plus 5 times so that you can reach out to 20. So this is an addition mainly. Right? So 4 multiplied by 5, it means actually multiple additions that you need to perform. So now if I can move out any of the code out of the block, just you see that this is the B3 before optimization or strength reduction, and this blue colored B3 after the strength reduction. And here I have moved out this code 4 star J with this 4 star J. I have moved this 4 star J, this multiplication operation out of the code, and in place of that I have added a static code over here, T4 equal to T4 minus 4. Not static, it is a dynamic though. And how I did it, I will be explaining that quite later, but you need to clear one idea that as I said that multiplication means addition multiple time. So let you, if you are using a loop and 4 multiplied by 5, so you are adding 4 5 times, right? So 5 times you are adding 4 and it is cumulatively, it is giving a value of 20, right? Now it is giving a value of 20. Now কিছু বলছেন? আসুন আসুন। Okay. what I was discussing, that you are adding 4 5 times. That means here if I use a loop, let I have used a for loop. So that means what is the complexity? Let the loop iterates for n times. Let, right. So the complexity of the loop is order of n. That is true. But at the same time, when you are putting a multiplication over the loop, you are multiplying the value with 5. The inner complexity 5 multiplied by 1, the for executing 4 asterisk 5. So for each operation you require one one CPU cycle. For 5 it requires 5 CPU cycle, right? So instead of doing that, if you can write 4 star 5, if you can write a 4 plus 5 for example, then definitely it will not be 5 star 1, it will be 1 star 1. What I wanted to mean, that inside a loop, if I can replace asterisk with plus or even division with minus, because asterisk and division, they are complex operators, but plus and minus, they are linear operators. Complex operators have higher complexities, but plus and minus have lower complexities. Why? I said now, minus means if you perform multiple subtraction, so there is a difference. Multiple subtraction, then it is a division. So it has a complexity of order of n, it has a order of 1, for example. Similarly, plus order of 1, it has an order of n. So my motive is, if I can move any code fragment which has a multiplication or division out of the code, then the strength of the entire block to be reduced, will be reduced. Okay. Same thing I have done here. You can just use an example. For example, you can put a value for j in this copy also I have shown. You can check, though it is not very prominent, but still you can check out here that if you can take the value j equal to 3, just I have given j equal to 3. Here also you can take j equal to 3. Using that, you can check out whether the values are coming accurately or not, because j equal to 3 means the first j equal to, it will be coming 3 minus 1, that means it is 2. T4, it will be coming 4 into j, 4 into 2, that is it is giving 12, sorry 8. Then T5 you are doing here, it will be a T4, it will be a into T4 in the sense a8. Here also, if you calculate T4 equal to 4 star j in the beginning, then on the beginning, what is the value for T4? It is 4 star j, means 4 into j means you have taken 3, that means it is 12. Then inside the block starts level 1, j equal to j minus 1. What is the j value? 3. So 3 minus 1 means 2. Second is T4. T4 equal to T4 minus 4. What is the T4 value? It is 12. 12 minus 4, it is 8. Then T5. The T5, it is equal to a minus a T4. A into T4 equal to a8. Just you see, both the codes are same. Here inside the loop, the codes and the values I am obtaining as the same. And this instruction T4 equal to 4 asterisk 3, I have moved out the code out of the, I have moved this code out of the block, and somehow I have reduced the strength. Right. Fine. Okay. Now the next part is induction variable elimination. Okay. So I hope now it is being clear to you that how the strength is being reduced for a code. Correct? Strength reduction means I have to replace, if it is possible, the asterisk operator with division or minus operator, or division operator with minus or plus operator, where it is being and the expression should be equivalent inside a loop, and so that the execution of the loop can be fast. Because you see, in this loop, once I move this 4 star j, somehow the complexity is being reduced with respect to this B3 block. Both the block B3 are here, but its complexity is being reduced. Right. Now I am moving to the last one, that is called induction variable elimination. Induction variable elimination, and that is actually it is the outcome of the strength reduction phase. You just check it here, that for B3 and let me copy it so that you can see it clearly. I hope you can see that this was the code segment that I have that we obtained after B3. So before performing strength reduction, this was B3. After strength reduction, this is the B3. Right. Now over B3, what we can do, that induction variable elimination. Right. Induction variable means, you see that in that code, J here, see that here the code was B3, that this B3 is same as the B3 that I have shown here. I'm marking it as a has. This is the B3, correct? And I'm taking only the inner block part, correct? Not I am taking the 4*J segment, because 4*J is already here. 4 asterisk J. It was assigned to T4. It was assigned to T4 equal to 4*J. Right. Now you see throughout the code, this J variable was independent of the block, because here the condition is T5 is greater than V. Then go to L1. So in the conditions, I can find it out that this J variable is nowhere related to the condition for the iteration of the block. If a variable is not contributing in the condition checking of a block, then it is better to move out the code out of the block, so that again I can reduce the CPU cycle. Because this J equal to J minus 1, if I repeat it n time, so it complexity will be order of n. But definitely if I can reduce this J to J minus 1 out of the block, then definitely I can reduce some sort of CPU cycle in terms of order of n. Right. So this is called induction variable elimination. If I can move out any variable out of the block, then I will do it. So this is the main thing you have to remember. So what different segments we have seen? We have seen the induction variable elimination. We have seen strength reduction. Induction variable means additional variables. If it is not required inside the loop, I can move out it out of the loop. Right. Over B3, and finally this B3 block is being generated, right? And in my copy also you can find that once all the optimization is being done, this is the final structure I also have given, right? This is the final structure for the same block that I have taken. I can remember we performed the optimization in B5 and B6. You can remember in the very first case. We also have performed optimization in B3 also. This is being done. And some optimizations are also being performed over here. Over here also you can check that, and I hope that you may have not you may be wondering that why is the code of J equal to J minus 1? It was a static code, J equal to J minus 1. That's why J equal to J minus 1 to be placed somewhere where it is not being required, correct? So it was not required throughout the code. So that's why we have eliminated it in a subsequent stage. Okay, so this is a final structure. You can obtain it over here, and subsequently you can go through this document that I have shared. In today's class, mostly we have covered the 3-address code and how the graph can be optimized using the directed acyclic graph method. Then the different stages of optimization. Just I'm quickly summarizing here. Common sub-expression elimination, copy propagation, dead code optimization, dead code removal, and loop optimization. Under the loop optimization, all the 3 segments we have seen. And I hope up to that it is fine, and you can some of the theoretical parts are also there. You can see from book also. That's all about your this intermediate code generation and code optimization segment. If you have further doubt, you can contact me again. Okay. So let me thank you very much for you all and best of luck for your examination.